Hi there. This video is going to serve as a short review for our first midterm. I sent out an email requesting some topics that people would like to see on a midterm review, and I gave a list of suggestions that you will see on the screen. And I took the top three most popular topics, and I made some example problems out of them, and I'm going to go over sort of my approach, my suggestions, and of course, do some example problems so you can get some more practice on these particular topics. The topics I'm going to be going over today are shortcut rules, including the product and quotient rules, and also including the chain rule. And lastly, I'm going to be talking about how to describe the meaning of the derivative in context, like, with a real contextual meaning with sentences and things like that. Okay, so let's get started on the shortcut rules, starting off with the product and quotient rules. Just before I even start doing the problems and explaining the process, let me remind you that our exam is open note, so you can certainly have your notes, including formula sheets. I have made a formula sheet available on Canvas that lists the common derivative formulas that you'll need to know for this class. And so you have something like this perhaps handy so that if you can't quite remember a derivative formula, you can look it up and apply it on the test questions. So I'm going to be using those. I've memorized them, so I don't need to go back and forth, but I'll refer to that periodically throughout this video. Okay, so the first example, we're trying to find the derivative of x cubed secant x. If you remember back to your pre-calculus training, x cubed is a type of function called a polynomial function. Secant is a type of function called a trigonometric function. These are two different kinds of functions. We're not going to be able to combine them together or simplify them, and they are adjacent to each other. They are next to each other with no plus sign or minus sign or anything, so the default means they are multiplied. And multiplication requires a special formula if you're going to find the derivative, and that's called the product rule. That's when you multiply two functions together. Multiply functions. This is not for when you're multiplying a constant. So they're multiplying functions, things with x's in them that move, that change value. All right. So the next kind of thing I'll point out is that with these more complicated problems, and they do get more and more complicated, it's hard to keep track of all the steps in one's head. So depending on your comfort level, I would definitely recommend you get used to writing out what you're going to do before you actually do it. Maybe this problem you're okay with doing in your head, but I'm going to write out the steps as a demo problem. And I suggest you do that also so that you're used to this process when you get to more complicated problems that kind of necessitate it. All right. So in order to find the derivative is the derivative is the ddx of y. That's the derivative, but we just call that dy dx. We just move the y up here next to the top d. So that's sort of the noun, dy dx, the derivative is equal to. And I would have to differentiate this side over here. And this is the multiplication of two things. So the multiplication rule, the product rule, is I differentiate the first expression and I multiply it by the second one. And then I add to that the derivative of the second function times the first one. So here, x cubed is the first function. So the derivative of, are you going to go away from me? There we go. The derivative of the first function, x cubed, times the second, plus the derivative of the second function, which is secant, times the first. All right, so that's my plan. And then I'm going to go ahead and do the derivatives. So the derivative of x cubed, that's the power rule. That's 3x squared. It's one of our more popular rules on the formula sheets. And then derivative of secant is secant tangent times x cubed. Now, these two terms are different. They consist of different functions, and so you can't really combine them together. They'd have to be the same object in order to add them. If you would like, you can try to factor. That's something that I know people who write math books really like doing, and a lot of math students like doing it too. So I will show you factoring. So we look to see what's common. There are polynomials that are common, and there's trig functions that are common. So I'll just factor out the common things. So this would be x squared secant x. Always factor out the smaller number of things. So there's two x's and one secant, so I'll factor this out. If I factor out and divide out by the x squared secant x, I'm left with 3. And over here, I get rid of the secant x, get rid of the x squared, factor them out essentially, and I'm left with x tangent x. All right, so that is the derivative, also simplified by factoring. Okay, next problem. This is an example of the quotient rule. Quotient rule is the sort of math term for when we're dividing two functions. So this is a function on top, an exponential 2 to the x, and a function on the bottom. It's a combination of a linear function and a trigonometric function. So this here is different functions that cannot be simplified. So we're going to have to use the quotient rule, right? So the quotient rule starts off a little bit like the product rule. So let me just write it down here. So quotient rule, we do the derivative of the first function or the top function times the bottom function, and then we reverse that. Derivative of the bottom function times the top. There is a minus sign in between, unlike a plus sign for the product rule. And on the bottom, we get the bottom function g squared. So f is the top function, g is the bottom function. So once again, I'll write out my plan for this one right here. So the derivative dy dx is going to be the derivative of the top function. Top function is 2 to the x times the bottom function minus the derivative of the bottom function times the top function. And this whole thing is divided by the bottom function starts with a 3, the bottom function squared. So there's my plan. And then I just have to do sort of the steps that I've laid out. There's essentially one derivative over here and in the beginning, and there's another derivative over here, sort of in the middle. And as long as I can keep track of everything, then I will be able to find my derivative dy dx. All right, 2 to the x is an exponential function, and according to my formula sheet, the derivative of exponential is 2 to the x times the natural log of the base. And then I'm multiplying by this 3 minus 4 sine x. All right, and then the derivative of 3 minus 4 sine x, the derivative of sum or difference of two things, we can differentiate them separately. So I can differentiate the 3, and then I can differentiate the 4 sine theta and just subtract the results. All right, the derivative of 3, the derivative of constant is 0 because constants don't move, and the derivative measures how fast something is moving. The derivative of a constant times a function, well, you don't have to use the product rule because it's not a function times a function. The derivative of a constant times a function, the constant doesn't get affected by the derivative, but I do have to differentiate the function part, which is the sine x. The derivative of sine x, if you remember, is cosine x. And then that's times 2 to the x. And this whole darn thing is still being divided by 3 minus 4 sine x squared. All right, so now all we do is just do some simplification, and then we're done with this problem. I don't require a lot of simplification on the midterms, but things that you need to simplify, things that can be combined together, Like terms that can be added or multiplied, things like that, I would like you to do for full credit. Over here, the only thing I can see is that there's a 0, and we can combine the 0 with anything because 0 times something, or 0 plus or minus something, is itself. So we have 2 to the x, ln 2, 3 minus 4 sine x, and then I lost my minus sign. So let me see where I lost my minus sign. Sorry about that, folks. So going back up a step, the root of the first times the second minus, maybe this is a minus sign. So that was supposed to be minus sign right there. Root of the first times the second minus the root of the second times the first. So let me change my error and make sure this is a minus sign. And then the root of the second times the first. Yeah, I just wrote a dot. Maybe I tried to write a minus sign and my pen didn't work quite right. But, checking your steps and finding corrections, that is a big part of math. So that is the part and parcel of what you sign up for, is go carefully and check for mistakes. I know it's a subtraction up there somewhere, so there's the subtraction. All right, and then 0 minus something is just that thing. So minus 4 cosine x, and then that's times 2 to the x. And then it's over this bottom function squared. Now I did notice that we have a couple of minus signs. We have minus and negative. Minus and negative can be combined together because it's two negatives multiplied, two negative ones multiplied. That's a positive. So I can rewrite this thing using a positive instead of a negative. And if you'd like, you can factor things out. There's a 2 to the x, which is common, and a 2 to the x, which is common on the top between the two terms. This parentheses thing, 3 minus 4 sine x, is different than this parentheses thing. So that's not the same. We can't factor that. The only thing factorable is the 2 to the x. So let me factor that out. Here we have ln 2, 3 minus 4 sine x. Some people would like to multiply that out. I'm not going to do every possible simplification. It's not necessary to multiply it out, but certainly some people would want to do that. Minus 4 is plus 4 cosine x, 2 to the x, and we get, of course, this bottom thing still being squared. All right, so this is an example of a nice, overly simplified version of the derivative using the quotient rule. Okay, let's go to our next page. So I'm going to do some chain rule problems. Chain rule is probably the most important rule you will learn in Calc 1, believe it or not. It has so many applications that currently most of you are unaware of because you're just learning it. But we're going to use the chain rule to do lots and lots of applications in this class, surprisingly so. Okay, so please, if you want to get good at something, get good at the chain rule. So the chain rule is essentially what happens when you have a composition of functions. So here I have a sine function. You can see sine. And I also have x and x cubed and e to the negative x. Those are polynomial and exponential functions. And I am not multiplying the sine x times those other functions. It's not a multiplication problem. It's a composition problem. So it's sine of these things. So I've taken these things and I've put them in place of where you might find x. So normally you might think of this as a sine function with something like x or theta or something in the middle. That's the kind of thing we see in terms of sines. But in place of that x, we have a totally different function. We have an x plus x cubed e to the negative x. So this is the perfect time to use the chain rule when we have something in place of x, what the textbook calls the inside function, but essentially what's the function that's replaced the normal place you would find x. So the way the chain rule works is you differentiate the function as if the interior part, that new function, was itself just like a variable x. So we're going to get cosine of the inside function. The inside function is not x. The inside function is this x plus x cubed e to the negative x, so it's going to be cosine of that thing. You just differentiate it normally, just imagining that this is your inside variable, even though it looks like a combination of things. The way chain rule works is that's just a single variable, oftentimes written as u. So we take the derivative of that function just as if it's a variable. Then we multiply by the derivative of that inside composition, that function that's replacing x. So what does that look like in terms of our strategy, in terms of our plan? All right, so to do this, we're going to differentiate the sign. So dy dx. The derivative sign is cosine, and then we're going to multiply by the derivative of whatever's inside the parentheses. So the interior function, the composition function, is x. Oops, I want a different color there. X plus x cubed e to the negative x. So that's the one that's replacing the x, and then we just do the derivative of that same inside function. So there's my plan. Differentiate sine, I got cosine, and then I multiply by the derivative of that inside function. All right, so dy dx. So I get cosine of this critter times the derivative of this thing. All right, well, it's a sum of two functions. So I could just differentiate each part separately. So I can differentiate the x, and I can differentiate this x cubed e to the negative x and just add the results together. All right, so what is the derivative of x? Well, that's a polynomial function. It's a line with slope 1, so its derivative is 1. And then what is the derivative of x cubed e to the negative x? Well, that is two functions being multiplied by each other. So that's going to require the product rule. So I do the derivative of the first times the second plus the derivative of the second times the first. And mind you, it's the cosine part over here times this derivative. And if you don't use parentheses, you may get confused and think it's only cosine times this first part, but this entire thing represents the derivative of the inside. So I highly recommend you put some parentheses here. Otherwise, you may forget that it's that entire thing, that entire derivative multiplied by the cosine x plus x cubed e to the negative x. All right, I'm not sure if I have enough room here, but we'll make it work. This part's done. Times 1 plus the derivative of x cubed is just 3x squared. That's our power rule. Okay, the derivative of e to the negative x. So this is not one of the elementary functions. It's not one of the functions on our formula sheet. This is closest to something like e to the x. E to the x is on our formula sheet, and the derivative of e to the x is itself. It's the only function whose derivative is exactly equal to itself. So this is e to a thing. This is e to something that's replaced x. I know it's a very minor replacement, like negative x is almost x, but it's not x. So we should use the chain rule. So to differentiate e to a thing, we use our formula. So we're going to get e to the thing times the derivative of that thing. I'm using the word thing to kind of emphasize like the inside function or what we've replaced x by. In this case, the thing we've replaced x by is negative x. So there should be a negative x here, and there should be a negative x here. So that's the derivative of e to the negative x. It is another chain rule. So there's a chain rule inside the chain rule here. And then I'm multiplying by x cubed. And then I'm ending my parentheses. All right, well, I think I'm almost done. All right, so maybe one of the things I'm also demonstrating is that These problems can take a lot of steps, and there's a lot of opportunity to make little mistakes. So try to go slow and steady, wins the race. All right, e to the negative x. I finally got to where I have to do the next derivative. The derivative of negative x is -1, and then I multiply by x cubed. Again, there's not much I could do. I could factor out an e to the negative x. Oh no, I can't because there's a 1 plus here. So each term has to have the same thing. So there's a 1 here. And there's no e to the x there. So there's e to the negative x in the second two terms and not e to the x in the first term. So I couldn't factor that. I mean, there are probably some ways I could do some sneaky factoring. It is not necessary. The one thing I would like you to do is combine this -1 with any other numbers, combine the numbers together. There's a -1 and a +1 over here. So what I'm going to do is, because I'm out of space, I'm just going to multiply -1 times +1, and we're going to write this as a minus here. And I'll just move over the x cubed so it looks prettier. Come on, pen. Here we go. All right. So hopefully that is the correct method. I have to go slow because even though I've been doing this for 40 years, it's still easy to make little mistakes. So double check. All right. Oh, so I did make a mistake. I don't know if anyone noticed that. I was trying to figure out why the 1 is out there because I did think this was factoring. And I think this is kind of ironic because I did warn people about using parentheses. And then immediately afterwards, I honestly forgot my own parentheses. So it's the derivative of this guy right here, right? So the derivative of this thing is, oh no, that's right. Okay, so I'm still second guessing myself. Apologize for not editing this, but it's kind of nice to see me live trying to fact check everything I'm doing. So I was thinking like there may be parentheses here, and I was going to explain why. And then when I was trying to explain why, I realized there's not parentheses there because the derivative of x is just 1, and the derivative of this thing is where I multiply. So there's the derivative of this thing, and I multiply by the derivative of that. So it's 1 plus that derivative. Okay, so let's assume that I've done all my due diligence and seeing if I found any of my errors. And we'll say that this is the answer. All right, you'll let me know if I made a mistake. Okay, part B. Just some more examples of the chain rule. Trying to get different things across and show you sort of a step-by-step process. So we can see a sine function and we can see some inside things, but there's also this 3 hanging out there. And that is sine raised to the third power. So it's this entire thing raised to the third power. So this kind of should evoke kind of an idea of thing being raised to the third. It's some great thing which has sines and x squareds and stuff like that raised to the third exponent. So that is our outside function. That's the function where normally we might see x raised to the third, but now we have something like sine or something else raised to the third. So how do we differentiate x to the third? Well, the derivative is 3x squared. I mean, normally there'd be an x in here, but our inside function is not x. So we are going to write in our inside function here. That's the sine thing. But of course, since we're not using x, we need to multiply by the derivative of this inside function, of this specifically sine x squared plus e to the negative x. All right, so that's a chain rule, right? Derivative of x cubed or thing cubed times the derivative of a thing. All right. This first part's been done. And now I have to differentiate this sort of inside function. So now I need to look at this. This is sine of some thing in parentheses. Oops, I guess I need another parentheses here. So that's sine of some stuff. So we want to be thinking of sine of stuff. Normally you might see an x in here, but we have some other stuff instead. So the derivative of sine thing, well, what is that? The derivative of sine thing is cosine thing times the derivative of the thing. That's the chain rule. And what is our thing this time? Well, our thing is this x squared plus e to negative x. And I put it in both places here. Cosine thing times the derivative of the thing. Okay, and then I keep going until I have finished all the steps. This first part is still the same, has not changed. The second part with cosine, I did that derivative already, so that part's done. And now I have to differentiate x squared plus e to negative x. There's a sum here, so I can differentiate each thing separately. So the derivative of x squared is 2x. And the derivative of e to x we just did, but to remind you, this is e to a thing, right? So to differentiate e to a thing, we have to use the rule for e to the x. So you got to think about e to the x as your sort of type of function we're differentiating. So what is the derivative of e to the thing? Derivative of e to the thing is e to the thing times the derivative of the thing. And our thing in this case is just negative x. As I said, this is similar to what we did in the previous problem. All right, so what do we got here? Well, we got a lack of space once again. But in terms of the math, actually, I don't really need an extra parentheses. I guess I do because there's a big parenthesis at the end. Okay, let me double check here. 3 sine this thing times the derivative of this. And the derivative of this is going to be cosine times this. So let me just put parentheses just to make sure I don't mess up because I did that potentially before. So 3 sine thing to the second power times the derivative of that sine thing. So I'll use parentheses to emphasize that entire thing is multiplied by the 3 sine thing squared. I forgot my square here too. Sorry about those little things, but that is, of course, what happens. So 3 sine thing squared times this entire derivative. That's going to be the cosine of the thing times the derivative of the thing. So let me use my parentheses here. Cosine of the thing times the derivative of the thing. And this thing here is 2x plus this, so I need parentheses for this. And then I need this times, well, -1, because the derivative of negative x is -1. All right, so once again, double checking and maybe finding some potential missing parentheses. I'm not sure they were necessary, but I'm going to put them in just to emphasize. So there's the sine, there's the 3. Oh, and I fact checked my 2 as well, so I forgot the 2 eventually. So there's the 3 thing, the thing cubed differentiated, which is 3 things squared, times this old mess. So this first part is the cosine, and then I'm going to multiply by the second part. This thing over here, the derivative of negative x, is -1. So it's going to be 2x. And instead of plus this thing times -1, I'll just do minus e to the negative x, like that. Then I need to close that parentheses like that. All right. Well, I think that's good enough. Again, there's not much we can do here. I guess I could multiply out, distribute out, this kind of thing. I'm not really sure that's going to do much. So you can experiment a little bit if you want with trying to simplify this. It's not necessary. I just want you to simplify it like things, certainly constants, like terms, exponentials that can be combined together. Other than that, I'm really trying to focus on getting the correct derivative. So this appears to be the answer for part B. All right, so for part C, more chain rule, of course. So I'll do this one with a little bit, maybe fewer explanations, and just kind of go into the mantra of, derivative of thing time, or, derivative e to the thing times the thing, kind of like this. So this is e to thing. So the derivative, let me use a different color here. The derivative will be e to the thing times the derivative of the thing. All right, if you remember, we don't really have formulas for square roots, but equivalent to a square root is the 1/2 exponent. So I'm just going to write this as the 1/2 exponent instead of using a square root. Then I can apply my power rule. All right, so I got my derivative. I got my e thing. Then I have derivative of thing to the 1/2. The derivative of thing to the 1/2 is 1/2 thing to the negative 1/2 times the derivative of the thing. Okay. Let me use some parentheses around this just to make sure that I didn't mess up anywhere with distributing or anything like that. Okay. So derivative, I get my square root thing. I get this whole thing, which I've done already. And then I have to differentiate this new function. The derivative of x to the 4th is 4x cubed. The derivative of sine thing is cosine thing times the derivative of thing. All right, and this derivative of x cubed, we know, is just 3x squared. So I think this will be the last derivative I have to take in this multi-step chain rule. So a lot of time just writing stuff down. But someone tells you math is not tedious, they're not really doing math. So a lot of just little steps you got to keep track of. And that is just the course that is. All right, so what do we got here? We got 4x cubed minus cosine x cubed. Can you move this a bit? Can you move over for me? Maybe not. Okay. There we go. Times the derivative of x cubed, which is 3x squared. Yeah, like that. Okay, so that's my long, crazy derivative. So we do want you to be able to like manage multiple chain rules and product rules inside chain rules and all kinds of stuff for demonstrating the knowledge of the chain rule and product rule and quotient rule, all those other things. All right, what can I possibly do to simplify this? Is there anything I can combine together? This is a trig function times a polynomial function, so that cannot be combined together. I guess I could factor out an x squared out of these two terms, because there's two terms separated by a plus sign or a minus sign, and they both contain an x squared. If you really wanted to, you could factor an x squared out of that. I'm not really sure that's going to be that helpful. I think there's nothing I could see that can be combined together. So I will consider this problem done. All right, so you can see this is going to be a longer video than often other ones, just because it just takes so long to do each of these complicated derivative formulas. So if you see something like this on the midterm, don't think it's going to be like a 3-minute question. It's probably going to take 10 minutes to go through step by step, making sure that you don't miss any mistakes, don't make any mistakes or miss any parts or whatever. So make sure that you kind of go slow and steady. And you get the right answer. All right, the last topic for the review is explaining the meaning of the derivative in some context. So we want you to be able to explain very precisely and accurately what the derivative means in a word problem. So we can find the derivative is 3x squared, or we can find the derivative is 7 or something like that. We want you to explain what that means, not just be able to algorithmically find it. So in these particular problems, we're going to be calculating the derivative at a particular point. And I'm going to remind you that the derivative at a point is the instantaneous rate of change at that point. So that's the definition of the derivative point. It's the instantaneous rate of change. Let's break down what we mean by the instantaneous rate of change. Okay, so the first thing is, what is a rate? A rate is how two related quantities are changing in relationship to each other. And specifically, we describe how the y variable is changing. And that's the top part of our fraction, right? Our change is delta y over delta x, right? So for example, this first one right here, 50 miles per hour, that means that we have an additional 50 miles for every 1 hour. You can think of this as 50 over 1 if you want to think of the 1 hour on the bottom. So for every 1 hour, we have an additional or an extra or an added 50 miles. Math people oftentimes talk about increasing and decreasing instead of going into that longer sentence. So we could say that there's an increase of 50 miles for each hour. So that's kind of an idea of a rate. For the second problem here, we're also have an increase here, right? So this is an increase of 4/3 dollars per pound. You can also think of this as a fraction with $4 over 3 pounds, because mathematically that's the same. And now your explanation would be there's an increase of $4 for every 3 pounds. So an increase of 4/3 dollars per 1 pound, or an increase of $4 for each 3 pounds. So that's how we talk about rates. And just to clarify, when we have a negative, we don't say the rate is negative. We interpret that as a decreasing. So something is decreasing. So what's decreasing here? Well, always we talk about how the y variable is increasing or decreasing, the y variable being on top. So there's a decrease of 5 miles per hour for each additional 1 hour. Remember, we can always think of this as over 1. So for every 1 hour, there's a decrease of 5 miles per hour. So that's what we mean by a rate. Just rate by itself is how two related quantities are changing, specifically describing how the y variable is changing with respect to the bottom variable x. And I have a couple notes here just to remind folks, you should specify increasing or decreasing. You shouldn't just say changes, because we know whether the change is increase or decrease. And also we should include always the correct numbers and units. So it shouldn't be vague. There's an increase of a certain number of miles per hour. It's an increase of specifically of 50. And you can't just say the increase is 50, because we want to know 50 watts. So make sure to include the numbers and the units in your explanation. All right, so that's what a rate is. What is an instantaneous rate? An instantaneous rate, also called the derivative, is a rate that occurs at a specific moment in time, or a specific moment. So the derivative at a point is how two quantities are changing at a specific moment. Your explanation should include whether it's increasing or decreasing with all the relevant numbers and units. Let me do a couple of examples so you can see this sort of in action. Okay. So my example A, I'm not going to have us calculate stuff. I'm just going to give you the relevant information. So I have the input variable X. It measures days since my birthday. And with the output variable Y, it measures money in my bank in dollars. And we're going to interpret the meaning of y prime of 10 equals -3. This is the derivative. This is dy dx. Oops, where's my color? This is dy dx at the inside thing is x, so x equals 10, and the derivative is equal to -3. So this inside thing, this 10, is the moment in time. So 10 watts. Well, you have to know what x is measured in, and x is measured in days. So 10 days. So something happens on day 10 or after 10 days, right? At 10 days, something's happening. What's happening? Well, the derivative is equal to -3. The derivative is how y is changing. Y is money. So this is dollars, but it's in relationship to x. So it's how the dollars are changing per x, which is per day. All right, so we need to put this together, right? So we need the moment in time, which is 10 days. So I could start off my sentence by saying 10 days after my birthday, because that's what the 10 means. So what's happening 10 days after my birthday? Well, something is changing. What's changing? Well, the y variable is changing. What is the y variable? The money in my bank. So 10 days after my birthday, let me just make some more space here just in case. 10 days after my birthday, comma, the money in my bank the negative means it decreases. And how much is it decreased by? It decreases by, well, the derivative amount is 3, so it decreases by $3 each one day. So at this moment in time, which is 10 days after my birthday, the money in my bank account is decreasing at the rate of $3 each one day. That doesn't mean like 3 days later it'll decrease by $1 or whatever. It just doesn't carry on. The rate could change, but at that moment of 10 days after my birthday, the money in my bank account is now decreasing by $3 at the rate of $3 each one day. All right, maybe I'll just write that in there just so that I don't mislead anyone. I'll write the extra thing I just said verbally by the rate or at the rate. I'm not sure about the English grammar here. Either by or at the rate of $3 for each day. Okay. I mean, English is a flexible language, so there are many ways of writing out the sentence, but they should all have that format. When is this happening? What's changing? Does it go up or does it go down? And how much exactly does it go up or down? And per what? Per day, per what? So that's the idea of our explanation of the derivative in context. All right, we'll do a couple more examples and then we'll end the review. All right, so the second example here, X is measuring a dollar spent on advertising, and Y is measuring the profits. These are both going to be measured in dollars. So money spent on advertising is dollars, company profits are in dollars. So the units here both have dollars on the top and dollars on the bottom. So we're going to explain this thing right here. The inside variable is the X. The outside variable is not the Y. Even though this looks like y, remember y prime is the not so great abbreviation for dy dx. So this is an x value of 1 million and a derivative value of 10. So this is one of the reasons why y prime is not good notation, because students routinely see 10 as a y value, and it is not as a y prime value. All right, so we have now an X value of 1 million, which is 1 million what's $1 million spent on advertising. So at the moment, $1 million is spent on advertising. We have something that's changing. What's changing? The Y is changing, which is the profits. The company profits are changing at that moment, right? So it's a little bit difficult to talk about a moment with money. So you might want to think about what a rate is, which is how things are changing. So in this particular case, I might recommend a grammar construction that talks about how each thing is changing. So instead of just saying 10 days after my birthday or when $1 million are spent on advertising, as we increase past $1 million, spent on advertising. So that's the moment in time. The moment in time is we're now about to go past the $1 million advertising. So at that moment that we start going past 1 million, so that kind of evokes an idea of X is changing, right? With time, humans always think of time as changing. So usually we get to say 10 days and, okay, well, the next time is going to be 11 days because, we just increment in time as we go on. So that's not really that ambiguous in example A. But example B, it seems a little bit harder to think about this. So I might want to put into there a little bit more about what's changing. So the changing is the amount of money spent on advertising. At the moment, we're spending $1 million. If we increase it by a certain amount, then something happens to the Y variable. So what is the Y variable? It's the profits. And are the profits going up or down? Well, they're going up because the derivative is positive, and it's positive 10. So as we increase the rent, or you increase the dollars spent on advertising past $1 million, the profit, the company profit, increases at the rate of $10 per $1. And this sounds confusing. What is $10 per dollar? So maybe I'll say $10 per dollar spent on advertising. So that clarifies it. Right. So at this moment in time, as we're increasing past $1 million spent on advertising, the company profit's going to increase at the rate of $10 per $1 spent on advertising. So that was a confusing one because it doesn't really include time in the way we naturally think of it. And it has the same units, top and bottom, dollars and dollars. So I thought I'd show you one that gave you a little bit of pause of how do we explain that in context. All right, one more example. And this one's a little bit more straightforward. In this particular example, we have Y representing my car speed measured in miles per hour. In terms of means what the X variable is. So the X variable is number of seconds after I see a police car in my rearview mirror. And so we got this F prime of 2 is equal to -5, which if you use the Leibniz notation, that means when you have an X value of -5, the derivative value is, the X is inside. When you have an X value of +2, then the derivative value is -5. So what is the +2? That is the X value. And what is X? It's the number of seconds after I see a police car. And what is the -5? Well, the -5 is the change in Y over the change in X. It's the derivative. And what is the Y variable measuring? Well, If you look carefully, the y variable is measuring in miles per hour. So this should be miles per hour. And what is the x variable measuring? Seconds again. So here's an example where the top y is essentially speed or velocity. It's miles per hour, right? So you're not always going to have a very simple unit, but you really don't have to understand all of these units. You just have to write them down. So it says the y variable is miles per hour. So whatever it is up there, you just write it there. You don't have to interpret it. You can interpret this as acceleration or something, but it's really not necessary. We're in a math class, so you could just say the y variable is miles per hour, the x variable seconds, and I'm going to write out my sentence as so. So we need a moment in time. So what's the moment in time? Well, that's the x value. So what is that? 2 seconds. So 2 seconds. What is the seconds measuring? Seconds after I see a police car in my rearview mirror. 2 seconds after I see a police car in my, that's a lot of writing, rear view mirror. So that's the moment in time. That's the instant. The instant is 2 seconds after I see a police car in my mirror. What's happening at this instant in time? Well, something's changing. What's changing? Well, the y is changing. So the y is miles per hour. So the miles per hour is changing. Is it increasing or decreasing? It is decreasing because there's a negative. How much is it increasing or decreasing? It's decreasing by 5. So the miles per hour is decreasing by 5. So 2 seconds after I see a police officer in my rearview mirror, my speed, my car's speed, you should put car in there. My car's speed is decreasing at the rate of 5 miles per hour. And I still need more because a rate is how y changes as x changes. So we forgot about the x here on the bottom. So there's a rate. The rate is 5 miles per hour for each 1 second. For each, I'll write additional just to emphasize, but I don't think that's necessary. 1 second. And I'm using the fact that I can just write this as 5/1 just to emphasize that it's a decrease of 5 miles per hour per 1 second. So this is my sentence that is sort of my interpretation, my explanation of what the derivative means in this particular context. 2 seconds after I see a police officer in my rearview mirror, my car speed is decreasing at the rate of 5 miles per hour for each additional second. So every second I'm slowing down 5 miles per hour. All right, well, thank you for watching this video all to the end. I hope it was helpful, enjoyable for you. Please reach out, let me know if I can help you with anything else for your exam preparation. And also, good luck on your exam.